So for those of you who were at the machine learning session today, this should hopefully that pretty smoothly. Those of you who weren't there know already a lot of the things that should be in the background of this, but we'll see. And it's really a pleasure to have Elizabeth DuPre present about NeuroImaging. Among her many accolades are the fact that she was a participant in NeuroHackademy in 2016. And is back here to teach. Has been back here to teach a couple of times and is now back to teach this. Thanks.
Thank you. Thanks, Ariel. Great. So thanks everyone so much for coming. I think the title of this was like machine learning with neuroimaging. So I'm going to tell you about machine learning with MRI. And I think that there's going to be some other speakers later in the week who are going to talk about other modalities. But I'm going to give a lot of emphasis on this one library, which I can tell we're already starting controversy. I say NeuroLearn. I think it's like a GIF thing. So, you know, but I'm on the development team now, so I think I have the right to say NeuroLearn at this point. But you know, we can talk about it. We can discuss maybe offline as we go, how we want to talk about this library. Anyway, I'm going to give an introduction to this library, and in the process, I'm going to talk about some of the general issues that come around when we're thinking about doing machine learning with neuroimaging. So there are 3 tabs I have open, which hopefully will all be useful to some degree. So one is Hub, where these notebooks all exist. They all exist in executed format. One thing I'll note is I misunderstood a little bit the composition of the drive. So if you try and just run it, it's not going to run. You'll need to remove the data dir, and then it will re-download the data into your personal user directory and run it there. That's going to be a little slow. So I don't necessarily encourage you to do it right now, especially because I don't think the server will love if every single person in this room pings it at the same time. So instead, what I'd encourage you to do is go through and you'll see that all of the outputs are already available here in the notebook. We'll talk about them and we'll look at the code and we can run it separately. I also generated a DuPre book, which is a really amazing tool where you take a collection of notebooks and create a website that's interactive and re-executable. So that is hosted on my personal GitHub, and I just have the local copy of that book here, which is what I'll be going through because I think it's a bit prettier to look at, and it also has all of the outputs. So that's what's going on, but if you want to follow along, I would encourage you to go on the hub in the curriculum under the DuPre NeuroLearn folder, I believe. That's where all the notebooks are. Perfect. Okay. So one thing I'll point out, in addition to the controversy around how to pronounce this word, is it may look somewhat familiar to those of you who've either worked with the library scikit-learn or heard of the library scikit-learn. You may say, that's interesting. It seems reminiscent of scikit-learn. And that isn't an accident. In fact, the teams that developed scikit-learn and NeuroLearn are partially overlapping. So a lot of the same developers floated between the 2 spaces, and they were really interested in developing this library to enable interacting with scikit-learn and with machine learning functionality for users coming from the neuroimaging domain, because there are a lot of data-specific considerations that we need to take in mind as neuroscientists that maybe if you have some tabular data, you don't need to think about right away. All right, so let's focus just on that for a second, the nature of neuroimaging data being non-tabular. So the question is essentially, when we think about machine learning pipelines, particularly those of you who were in Ariel's great tutorial yesterday, maybe saw or have seen in the past examples of using things like extracted free surfer values or data that's already been, survey data or something like that, where you have effectively tables of data and you're going to use machine learning algorithms on it. But when we're looking at neuroimaging data, we're not in that world. We're not in that ballpark, right? What you see actually are images. And it's important to know a couple of things about these images. One is just how to get an image into a table, non-obvious. 2 is there are features of these images, right? They have spatial and temporal dependencies between successive data points. So knowing where you are in the brain and at what point you are in the time series tells you something about the next point in the brain and the next point in the time series in a way that's not necessarily true with pure tabular data. And there's also the other piece, which is that when we look at, in my case, fMRI images, bold images, we know there's a lot of signal in there that's related to blood oxygen level dependent signal. We also know there's a lot of signal in there that's not. And so what we need to think about is, how do we separately conceive of our signal of interest and our signal of non-interest, which I'll call noise. And so we need to think about how, we have this very richly interdependent data. It has signal and it has noise. None of it seems to fit very clearly into a table. How are we going to interact with scikit-learn in a way that we usually would like to interact with? So what I'm going to argue is that NeuroLearn is playing a really crucial role in this ecosystem by bridging this space, by allowing us to take this kind of data and interact with scikit-learn style pipelines. Also, it does a lot of other fun things, which you'll see highlighted, some plotting and data set fetching and all kinds of fun stuff. But critically, its role fundamentally is focused on statistical and machine learning, enabling that with neuroimaging data. So to get a quick sense of the problem, the quickest method is always just to look at data, right? You should always look at your data. And you may have your own data set locally that you'd like to work with, but to make sure we're all on the same page, I'm going to recommend that we use a data set that NeuroLearn actually provides. And one thing to note first is anything that's distributed in NeuroLearn is something that's been made publicly accessible. So we always owe a huge debt for the people who have made their data publicly accessible. And today we're going to be using a data set that was originally collected by Rebecca Sachs's group at MIT and is hosted on OpenNeuro. And it's been pre-processed with fMRI prep and downsampled to a low resolution. So it's pretty snappy for our kind of little examples. You can learn a lot about the data set directly from the NeuroLearn documentation, but as an overview, it contains over 150 children and adults watching a short Pixar film. So we can download the first 30 participants. And if you're in the hub, this is the line that will cause trouble because it has a data dir parameter here. And that's not going to work for you because read-write permissions were things I didn't understand when I first set this up. So if you just run it like this, it'll download locally whenever you want to do that, not all at once. So if we fetch this, what it's going to do is it's going to fetch 30 of the 155 participants, and it's going to give us some information about them. In particular, it's going to have a phenotypic, which tells us whether or not they're children or adults, for example. And it's also going to have func, which provides access to the functional fMRI data. So we're going to use another favorite library that's also controversial in how you pronounce it. I call it NeuroBabel. So we're going to use NeuroBabel to load the first functional image and look at its shape. And we can see that, as promised, it's not a table. It looks a little more like a tensor. So we have these first 3 dimensions, somewhere between 50 to 60, and then one dimension that's 168. And what this means is that there's 168 volumes or time points, and each has a 3D structure of 50, 59, 50. So maybe you find that very useful. Maybe you just want an image. NeuroLearn luckily comes with a lot of plotting functionality to allow us to actually look at these images. And because each fMRI run is this 40 time series, as I mentioned, it has 168 volumes. We're going to subset the data. So we look at a single 3D image. And we're going to choose to do that using mean image. There's this other function, index image, that you could use. But effectively, this is just going to take the average image across our time series and allow us to plot it in an interactive viewer. So now we can get a sense for the data that we're actually thinking about when we have this question of how can we start doing machine learning on this? So as promised, what we'd like to do, I'm going to make this a little bit bigger, is figure out how to extract meaningful information. So importantly, we could work with the full time series directly. We could extract information from every single point on the brain and have the full time series and try and do analyses on that. We're lucky and not lucky in neuroimaging in that we work with very high dimensional data. So that's going to make our analyses quite complicated. So often for that reason and for some conceptual reasons as well, one thing we'd like to do is reduce the dimensionality of our data in a structured way. We want to find a low dimensional representation that preserves information that we think is important in the full data set. And so there are multiple ways to do that. One of which is really useful is to only consider signal within certain learned or predefined regions of interest. And we'll also be able to think about, okay, if we have signal in these predefined regions of interest, how do we take into account our known noise sources in that same signal? Luckily, NeuroLearn is really focused on this with a collection of objects called the masker objects. But to introduce them and kind of the range of objects that we have, let's first think about what masking fMRI is really doing. So if you see this illustration, okay, you can see my pointer hopefully. If you see this illustration, effectively what we have is you can think about every volume, or 168, remember, as a different little cube in time. And we have a mask, which isn't guaranteed to be perfectly cube-like. But we would like to use the mask to extract data from each of the volumes. And what we'd like to get out in the end is something that looks like this, which is exactly what scikit-learn expects, which is samples by features, right? So this is our whole goal. And essentially, excuse me, what we can imagine we're doing is overlaying a 3D grid on our brain images. Then our mask is going to tell us which cubes or voxels, like 3D pixels, we're sampling from. And because we're working with multiple volumes, we're going to overlay this at each point in time. Right? And so masker objects are really, really useful because they allow us to define these masks. They allow us to define many kinds of masks, which I'll tell you about in a minute. And NeuroLearn provides means to not only, take a region of interest that's predefined, but also to define your own. So in this tutorial, for ease of use, we're going to use MSDL, which is multi-subject dictionary learning. It's a predefined atlas, which defines a set of probabilistic ROIs across the brain. So for those who aren't familiar with this necessarily, when you think about a mask, we would call that a deterministic region of interest if it has like a clear 1, 0 value, if it is or isn't in the mask, but a probabilistic is closer to like an ICA map, right? So there's a weighting on something between 0 and 1 for some of the voxels. And this is nice because it allows you to have variability in the boundary of the region. So one of the other nice things is it comes directly in NeuroLearn. So we can just use datasets, fetch atlas, MSDL, multi-subject dictionary learning, and that's going to give us this atlas where we can then see region chords and the number of regions. And we see that we have 39 ROIs, which belong to a range of networks. So the cerebellum, the motor, language, temporal, salience. These are all from this particular atlas, which we defined in this paper, which I would encourage you to check out if you're interested. But again, this is just one atlas. NeuroLearn has many different options available, including the Schaefer Atlas and the Harvard-Oxford Atlas. And, there's a range in here, but you can, of course, always add your own. All right. So again, look at your data. What does this atlas actually do? What does it mean? How is it going to get us closer to our goal? Because remember, our goal is to get a version of the data that we can do machine learning on. So if we actually look at the atlas, it looks something like this. And importantly, we're using plot prob atlas because it's a probabilistic atlas. So we take the maps, we use plot prob atlas, and we can see kind of the range of ROI coverage that we have in the brain. So what we're going to do now is we're going to pair together this particular atlas with the masking procedure I told you earlier about from the masker objects. But I just want to make a digression to note that many people, when they see nifty masker objects for the first time, are like, why are there so many? And there are so many because there are many different kinds of regions of interest that you might be interested in. So for example, if you have a single region of interest, like say a gray matter mask, where you're like, this is my one region, it is gray matter. You may want to use something like Nifty Masker, because that's just going to apply that mask. However, if you have something like the Schaefer Atlas, or any atlas where you're like, here are all of my regions and each of them have hard boundaries, you'd want to use something like Nifty Labels Masker. But in our case, because we're working with soft or probabilistic ROIs, we're going to use Nifty Maps Masker. And there's work on hand to make a Nifty Surface Masker. This is stuff that's continuing to expand. So I would definitely refer you to the documentation as you keep going over the next months to see what's coming down the pipes next. But there's lots of really good maskers, so I would definitely recommend them. All right, and then I'll do this one thing and then I'll take a break for questions, because we can actually put these together. So if we do from NyLearn import maskers, these are Nifty Maps Masker, because remember, again, we have a probabilistic atlas in this particular case. We can say that we're going to use the multi-subject dictionary learning atlas maps as our mask. We're going to resample them to the data, and then we're going to provide some information that's relevant for this question of what is signal and what is noise. So we're going to say, what is the repetition time in our data set? Are we detrending that signal? And then we're going to supply a low and a high pass filter. And all of this can be done directly in the mask. Yes.
Hi, sorry, maybe it's a long answer, but so when using probabilistic or deterministic atlas, do you have maybe a certain reason behind it? For example, for this example, if there is kind of a certain hypothesis that's you're following it, that's why you chose it.
So for this particular example, the reason is that we're going to do a downstream. We're in the next notebook. We're going to. Sorry. Yeah. Good point. So the question was, how would you choose between a probabilistic and a deterministic atlas in general? And maybe in particular for this example, why would we do one or the other? So in this particular example, we're going to do in the next notebook a intersubject classification problem. And for that, it works out that the probabilistic atlas is going to get a bit more variability, which can be useful for that problem. But in general, the question is effectively, what kind of dimensionality reduction do you want to do on your signal? So in the same way that you would choose maybe differentially between having a region of interest or an ICA map, those are going to summarize the signal differently. And the ICA map is going to allow you to have more variability in the components versus the region of interest is just going to say, here's the anatomically or functionally or whatever defined mask as I view it, and I just want to see the signal within that. So I would say that in general, it does link to your question, and your question links quite broadly to this issue of like, what is the goal? And how can you use dimensionality reduction to best support whatever the goal is? And so if you're interested in something where you want to see variability, often using probabilistic atlases will help. And there are many more that I'm not showing here. For example, there's a really good paper which is written in support of one of the atlases in NyLearn called DeFumo, which is the Dictionary of Functional Modules, I believe. And there they do a really nice breakdown about like some of the cases where they find probabilistic atlases do better. So yes, it depends on your use case. I would point you to, depending on what you want to do, maybe see what other folks have found works well for dimensionality reduction. Okay, I just wanted to finish this paragraph, and then, sorry, I wanted to really get into questions, because this is kind of a punchline that I want to make sure we get. So effectively, what we're seeing is that if we take the Nifty Maps Masker, we supply the map from that atlas that we have, the multi-subject dictionary learning, we resample, we do these little parameters, which are going to allow us to think about noise in this context, right? Known sources of noise. And then we just call a dot fit, right? That's all we're going to do for now. And the reason I wanted to point this out is because this dot fit method is going to look super familiar if you've worked with scikit-learn estimators at all. Effectively, what we're seeing is that this is the same structure as what's used in scikit-learn, the same general API, but just carried over to the neuroimaging domain. And so it makes it really easy for us to start interfacing with scikit-learn pipelines. And we're not going to supply any data to this particular fit method. That's because we're fitting the masker to the provided ROIs rather than our data. But depending on the particular task you're doing, that's something to think about as well. Okay, I'll show you what that looks like in a minute. But first, let's take some questions. So yes.
This is like maybe technical, but so you're extracting the mean time series from the ROIs and then doing your filter?
No, you're doing the filter and then extracting.
Okay, so it does it on like a voxel wise basis
Yeah.
first? Oh, that's cool.
I think so. Yeah, I believe so. We can double check that. But it's
Do people care? I don't know.
people do care. So there's we in general try to adhere to best practice. I think this is something Ariel said about the scikit-learn library yesterday, which is generally true in NeuroImaging as well, which is that the development decisions are focused on methods that have been proven in terms of quality, but aren't necessarily the newest. So NeuroImaging is not necessarily the place to find the newest methods. It's the place to find the methods that have been shown to work really well and adhere to best practice. So I'm pretty sure we do that because I think that that's best practice. And yeah. But in general, that would be the line for NeuroImaging. Is it a well-established method that has been proven multiple times and meets current field best practice? What other questions do people have? Yes.
Yeah, I also got a somewhat technical question because some people argue that if you're filtering, you should be doing it at the moment that you're regressing out through confounds. And I assume that the data here is already like clean in some way. But is there a way to filter and have the confounds done at the same time and not like?
Yes. So we're building up an example, but later on we will absolutely talk about confounds. Yeah. Because effectively it's exactly this question of like when you're fitting it, how do you handle it all at once? So what we're doing right now, remember, is we're not actually fitting to any data. We're just fitting to the ROIs. So we're saying, when you give me data, these are the operations I will apply. So when you supply the data, if you supply the confounds at the same time, it's going to try and apply those all at once. But we haven't actually done any filtering to data here, remember, because the fit is empty. So this is just setting up the object that we'll use. Yeah.
Sorry.
No. You can kind of think of it like a Lambda function, but I think that it's more helpful. Like if you've used estimators in general in scikit-learn, it's more helpful to think of it in that context because it's really trying to follow the logic of a scikit-learn pipeline effectively, because this is designed to plug into that. But yeah, in general, maybe if you're not thinking in the scikit-learn framework, you could think about it like, oh, this is something that I can apply later in like a functional programming sense. But I would encourage you to think in the scikit-learn way, because that will in general give good intuitions for what NeuroImaging is doing. What other questions do people have? No? Okay, cool. All right, so now we're going to do what was promised. So remember, we haven't shown this any data. We've just given it some general guidelines for what we want. And now we can actually take this masker and transform. So again, using the scikit-learn conventions, our data. And here we're just going to transform the very first participant. We're not going to pass any confounds. That'll come later. So we know this is wrong, but it's also useful just to see the structure of how we make these calls. So when we transform using this, we get an ROI time series, and we see that now we've gone from 50, 59, 50, 168 to 168, 39. So what happened? Effectively, what we're doing is now, rather than providing information on every voxel within our original 3D grid, we're using a dimensionality reduction, which is in this case the probabilistic atlas, to only consider those voxels that fall within the 39 regions of interest provided by our atlas, aggregate within those. And so now we go from 50, 59, 50 to just 39 for our 39 provided ROIs. And we'll also see that the dimensions flipped, right? So maybe you expected it to be 39, 168, but it's actually 168, 39. And this is to make sure that we're following the scikit-learn convention that rows in a data matrix are samples and columns in a data matrix are features. This means that when you put things into scikit-learn or any machine learning pipeline that follows scikit-learn conventions, at which point there are now many, this will be the right orientation. So you don't have to worry about flipping your dimensions back and forth. This takes care of it for you. Okay, so if you're working with imaging data, you say, well, that's nice. I have these time series. What do I do with them? There are many things you could do with them at this point. One of the things I just want to highlight that you can do is to create a connectome. So what we're going to do is we're going to use something from NeuroImaging connectome called connectivity measure. And then we can say what kind we want. In this case, we're going to do correlation. In a little bit, I'll talk about some of the other kinds. But what's cool is we can just take those ROI time series that we already have, fit, transform them, again, a scikit-learn convention. So we're doing both in one step. And now we get a correlation matrix out. And we can actually just plot that using plot matrix from NeuroImaging. And we can see the functional connectivity as defined by correlation for all of our regions of interest. So we get this connectome for our data. And we can even view it on the brain using Plotly, which is also within NeuroImaging, as an embedded connectome. So you can see all of the different nodes and edges. So this is pretty cool because you can do this all with just a few lines. And as I'm going to show you, it makes it really easy to then set it up for, pass it in rather for machine learning analyses. All right, as promised, let's talk about confounds. That was a really beautiful brain, but quite connected, maybe like a little too connected. So maybe we should be a little suspicious. Maybe we should go back and look at our noise sources. So what can we do? As we've already seen, maskers are going to allow us to perform many useful operations beyond just masking, including some of the pre-processing that we know or processing that we know is important for measured signals of no interest, like drift, when we were thinking about so far, and also head motion is one that we often worry about a lot if you're working with fMRI data, or actually many kinds of neuroimaging data. So our development data set also includes several of these signals of no interest that were generated by fMRI prep. And we can access these with the confounds attribute that's directly provided with the data set. So if we load pandas and we look at the confounds and we load just the first few rows, we can see we've got the 6 classic motion parameters, translation and rotation in each of the 3 cardinal directions, frameways displacement, and some anatomical contour, the first 5, CSF and white matter. That's what happens to be in here. But of course, if you have your own data set, you could have any collection of confounds that you want, right? So this is a subset of what was generated in fMRI prep. You can also actually request the full fMRI prep output by passing reduced confounds equals false. But this is always dangerous unless you use load confounds or something else, because you don't want to pass all of the confounds to fMRI prep to any analysis. It's going to kill your degrees of freedom, and it's not necessarily going to get you what you want. So we made some executive decisions in this particular data set, but in general, there's a really nice functionality in NeuroImaging called load confounds that gives access to several best practice confound strategies. I would also encourage you to just think carefully about what you're including as confounds, because this will make a huge difference in your analysis. All right, so importantly, we can pass confounds directly to our masker objects, and this is going to allow us to do exactly what we want, whereas before we just defined that, hey, when I give you data, make sure to filter it. Now we say, hey, here's my data and here's my confounds. Make sure to take advantage of those when I'm actually extracting the data. So we do the masker transform, and again, we're just doing it for the first participant in this case, because it's a little bit easier to see everything on one than 155. So we do it for the first participant. We get this corrected correlation matrix by, again, using the correlation measure and fitting it on the corrected ROI time series. And then again, we can plot it. And as you can see, or maybe let's scroll up, as you can see now, This was the original matrix without confound correction, and this is the new matrix. And then here is it on the brain. Yes.
Why is the correlation of a region with itself 0?
So we masked that out. You'll notice that here. Sorry, I should have said that out loud. We did this NP fill diagonal 0, because otherwise what happens is that the correlation's 1 and then it skews all the correlation values. They're really hard to see. Yeah. Yes.
I'm sure when we created the master object where we put some pre-processing steps there and now we're putting compounds, how does it decide what to do first, then compounds or
Right. So yeah, good point. So this goes back to the question about like the steps in which things are done. So the best practice is to do them all at once. So it's not going to do like, when you remember, because we did the dot fit and we didn't supply any data, it's not doing anything to the data there. So when it actually gets the data, it's getting the confounds and the filtering and whatever else you request all at the same time. And it's trying to leverage those appropriately to do as much as possible at once. It's not gonna like first filter when you do the fit and then do the confounds if they're supplied later. The goal is to supply everything at one time. But good question. And yes, this is maybe something I should say just in general for open source code. One of the really nice things about open source code is it's open. So if you ever have a question about exactly what's happening, I would highly encourage you to go to the code and just load the masker and look at it and see like, okay, what is it doing for, this particular step? And then the best case outcome is you open an issue and say, hey, I think the documentation could be improved. Here's how I read what the code is doing. And I feel like the docs don't say that. That's a super valuable contribution. So definitely something to look out for. Perfect. Okay, so what's cool is now we see a big difference when we're including the confounds. And this is a really nice reminder that, again, our whole goal with this notebook was to get from neuroimaging data to something that could go in a pipeline. And there's a lot of question marks from A to Z. How do you choose the atlas? How do you know what confounds to include? This is a really nice framework to allow you to quickly see and iterate on what you're doing to try and get to best practice. And then you want to make sure you do this before you run your machine learning analyses effectively. You want to make sure that the features that you're putting into the machine learning analyses are appropriate so you can take them forward. So this kind of general framework with the many nifty maskers, if you want to do connectivity with the connectome class, is all very helpful. I promised you machine learning though, so maybe we should do some machine learning. All right. Do people have questions at this point before we dive in? And I apologize if there are any questions on Slack. I have Slack closed, otherwise it'll ping aggressively. So if there are, please just wave at me, someone. Okay, cool. So now that we've seen how to create a connectome for an individual subject, we're ready to think about how we can actually use this connectome or use our neuroimaging data in general for machine learning analyses. And in this particular example, we'll keep working with the same development data set, but now we'd like to see if we can predict age group, whether a participant is a child or adult, based on their connectome as defined by the functional connectivity matrix that we just made. And importantly, we're going to do a different kind of feature engineering here, quote unquote. We're going to see whether we're more or less accurate in our predictions based on how we define functional connectivity. Because I think, as Katarina Grattan said, this is one of maybe the most hated and misunderstood terms that you could have. And so there are many different ways that you can define functional connectivity, and we're going to see how our results vary depending on a few of them, right? In particular, we're going to keep things mostly the same. So we're going to use the same data set, we're going to use the same atlas, but we're going to do 3 different ways to define functional connectivity: correlation, partial correlation, and tangent space embedding. And I'll talk a little bit about those as we go. But the first thing we need to do is set up our minimal environment, which is going to include basically everything we did in the last notebook. In this case, we're going to keep subjects at 30. We're going to fit the same atlas, and then we're going to set broadly the same parameters to our masker, the same empty fit call, And then for the first one, just to show you, we're going to set kind to correlation. All right, but now, importantly, we should have a much better idea about what all of these steps are doing than we did in the last notebook. So we basically got the last notebook down to like a cell, which is pretty cool. But we're going to actually go through and build our data set. So we're going to take advantage of each of the 30 participants and extract a few relevant pieces of information, including their functional scan, their confound file, and whether they were a child or adult at this time of the scan. And then we're going to transform their data again using Nifty Maps Masker. And as we learned last time, it's really important to correct for known sources of noise. So we'll also pass the confounds file to clean up each subject's data. So this is all what we did before, but now we're going to do it with 30 participants. So we're basically going to say, if we zip all of these together, we can iterate through. We're going to transform our functional data, including the confounds. We're going to keep that time series around. And then if we know that they were a child based on their phenotypic data, we're going to duplicate it. This is not the most efficient, but I think it's quite clear. It's easy to follow what's happening. So we're going to duplicate it in a separate children only list. And then we're going to append, were they a child or adult into a groups list. That way we can keep track of all the participants' data and what we have. And we're going to print back how many children are in our particular sample of 30 that we've extracted from the remember, 155. And in this case, we see that we have 24 children, which is roughly proportional to the original participant pool, which had 122 children and 33 adults. So development data set is trying to be kind of smart and saying, okay, we're going to roughly preserve proportions depending on how many participants you request. So we now have a list. If you remember, this pooled subjects has every child and adult participant. And so if we look at the shape of any entry in it, we see exactly as we did before. Remember, it's n samples by n features. So it's 168 time points for each participant, the 39 ROIs of our multi-subject dictionary learning atlas. All right, first, because I promised you we'd use correlation first, let's use the most common kind of connectivity and the one that we used in the last section. So what we're going to see is it models the full marginal connectivity between pairwise ROIs. So it's going to expect a list of time series. So we directly supply the list of ROI time series we just created, and it will then compute individual correlation matrices. Remember, this is what we did last time. Last time we just gave it one participant. So now we're going to do a few. So what we can basically do is we have this list, which is all the children. We pass the list to correlation measure, and now it's going to give out a bunch of correlation matrices. And it tells me when I do that, that I have 24 for my 24 children, and each of them are 39 by 39. So all the shapes check out. Critically important, even when things are too, you can't visualize them, check the shapes. Always check the shapes because things can easily get flipped. You can lose a dimension and then you will get very confusing results. So definitely make sure at a minimum, check the shapes as you go. So this is a good sanity check. We see it's the right shape. We're in the right space. All right, one other cool thing we can do is like other scikit-learn estimators, you can have access to several attributes after it's fitted with this little whatever the attribute is underscore. So in our case, correlation measure has a mean. So we can use that to get our mean correlation matrix for all the children. And that's just going to have this shape of 39 by 39. So it tells us the average correlation matrix or the average connectivity matrix as measured by correlation across the 24 children. First, though, let's just look at the first three, just to see the variability that we have. And remember, these are all corrected for their respective confound files. And so we can see that there is some variability across the different child participants in terms of their correlation-based functional connectomes. And we can also display the connectome on the brain. Here, we're going to take advantage of that mean. Rather than showing a bunch of brains, we're just going to show the average overall of these 24 children. So this is kind of cool. We can see, we get a better sense of what our nodes and edges look like. But rather than only working with correlation, we can define other measures as well. Are there any questions about this first part? Because we're going to repeat it a couple times with different measures.
It's again very like technical, but I was just wondering, do you, by saying you only have 3 subplots, are you reducing
This one.
the for with just the 3 iterations? It's like you're putting in there the whole correlation.
Yeah, exactly. Yeah. So basically, we're just trying to look at the first 3. So we zip the correlation matrices and the axes, and we only set like a small number of axes. So when you zip things of unequal lengths, it's going to go to the smallest one.
Okay, so when they have separate like lengths, it will choose like the one with the lowest number.
Yeah, exactly. This is a general Python thing. So zip is like a general Python thing. And so if you zip together 2 iterables of unequal lengths, it will go to the lowest one. There are other functions in like iter tools, which is a built-in Python thing where you can have it repeat and do other fun stuff. But yeah. Yeah, of course. What other questions do people have? No? Okay, cool. Let's do it again. All right, so that was our full correlation. But again, functional connectivity, you can do other things. So what if we do partial correlations? So rather than looking at the full marginal connectivity, we're going to study partial correlation coefficients. And what this effectively does is it looks at one edge, so the connection between 2 nodes, controlling for other edges in the graph. So we're trying to look at effectively sometimes what's called direct connections revealed by partial correlation coefficients. So what's really cool is that we can do exactly what we did before. And the only thing we're going to change is this kind argument to connectivity measure. And now we're going to call it partial correlation. And because we do that, we now get different partial correlation matrices. And when we plot them using the same procedures above, you can see that they're much weaker than the full marginal connectivity from correlation. Again, just for the first 3 children in this case. We can also do the mean partial correlation connectome. We see that there are many, many fewer edges. It's a lot sparser of a graph, which again just shows you when you say functional connectivity, it's really important to be clear about what you mean and what you're using to define that, because it's going to have huge effects on what your graph looks like. All right. The last method I want to show you, and then I promise we are going to do some classification. The last method I want to show you is called tangent space embedding. So this is yet another alternative, because effectively what it's doing is using both correlations and partial correlations, but importantly, it's really functioning at the group level. So again, we can just change kind to tangent, fit it to all of the same children to get our tangent matrices. And what it's effectively doing is saying like, okay, I have my group model of connectivity. I'm going to consider individuals as perturbations off of this. So I want to see, you know, in this case, the mean doesn't really make sense to think about because that's sort of the center of the distribution. And all we're thinking about is how individual participants vary from that mean. So this is really cool because it gives you a way to say, in relation to the group, how does a given participant vary from that group? And is that meaningful? Rather than just within our other measures, we were looking within participants, what was the correlation? What was the partial correlation? So because we do that, we can't, it doesn't really make sense to plot the mean connectome because that's just going to be set to 0, but we can still plot the tangent offsets for the first 3 participants to look at those. And we see that those have even less structure than our previous method, the partial correlation method. So again, the metric that you use is going to strongly define the kind of connectome you get, and that's going to impact any downstream inferences. Yes.
What kind of perturbations is this inducing?
Right. Sorry. No, good point. So it's not inducing perturbations. It's considering individuals as perturbations off a group. So effectively, you're trying to say, I have my whole group of children. I set the mean, I compute the mean connectome. You can think about it this way. I compute the mean connectome and I set that to 0. And for each participant, for each edge, how different are they from the group? Are they more connected at that edge? Are they less connected at that edge? And I'm going to represent that change from the group as their particular connectome.
It's sort of like having distance.
Kind of, yeah. There's a really good paper actually that I think is cited in here where they introduce it in neuroimaging data. So yeah, I would definitely check that out if you want. Yeah, it's cited at the bottom. Definitely check that out if you want more detail in general on the method. What other questions do people have? Okay. All right, so we have all of these different ways that we can compute functional connectivity. And what we can actually do now is use these as features in a classification analysis. So we can say, I would like to learn a classifier that distinguishes based on the connectivity patterns, the functional connectome patterns, whether or not a given connectome belongs to a child or an adult. And what's really cool, the whole benefit of NeuroLearn is this is super easy to do in scikit-learn. This is designed to make it as seamless as possible to move from one to the other. So how are we going to do that? We have to have all the same considerations that we had with any other kind of machine learning, and I'll talk about some of them in the next notebook too. But one of which is we need a train and a test split, right? So what we're going to do is we're going to use stratified shuffle split, which is going to preserve the proportion of children to adults in the test set. And we're going to split it 15 times. And then we're going to compute classification accuracies for each of the different kinds of functional connectivity, excuse me. We've identified the correlation, partial correlation, and tangent space embedding. So here we can see what we're doing. If you've done a tabular data analysis with scikit-learn, this will look familiar. If you haven't, what's so cool is it's not that many lines of code. And they have great documentation explaining each line. So effectively what we're doing is we're importing accuracy score. This is going to allow us to assess, a metric of how well we did. Hence it's from metrics. From model selection, we're going to do stratified shuffle split, which is our cross-validation method, how we split things into train and test. And then from support vector machines, we're going to import a linear support vector classifier. Obviously, there are many other very powerful classifiers, but for the purposes of this, it's easier to start with something linear. Let's go with the simplest thing. And then we're going to say for kinds, you'll notice that these are the kinds of functional connectivity that we've explored earlier. So correlation, partial correlation, and tangent. And now we're going to do a little bit of data wrangling. So this is going to say how many groups are there. There's just 2 classes in this case. We're going to set our cross-validation using stratified shuffle split, as I promised you, 15 times. We're going to set our test size to 5. And because this is randomly shuffling, we need to set a random state for reproducibility. And then we're just going to convert this to an array. All right, so now what we're going to do is on each fold of our cross-validation, we're going to train the scikit-learn linear support vector classifier estimator to run on our training set of participants and apply it to our test set. So how do we do it? For each kind in kind, so for every kind of functional connectivity, we're going to go through this loop. Yes.
I guess it doesn't matter, but we pull 30 people and 24 are one group and 6 are good. So there'll be polls where it will be completely one group of kids.
That's a great question. So the question is, we only pulled 30 people, 24 are children. And so if we just do it 15 times, aren't we going to get a lot of folds that are only children? So that's where understanding the cross-validation method you're using is super important. So then in this case, what we're doing is stratified shuffle split. So stratified shuffle split is going to stratify to make sure the same proportion of the different groups are present because we have a really big class imbalance. And shuffle split means that it's going to split it, but it's going to shuffle it so participants can appear across folds. So like you'll never get the same participant in train and test, but from training fold 1 to training fold 2, there could be a participant that reappears, and that's going to have to happen with the adults so that we can make sure we maintain our proportions. Other cross-validation methods don't give you that guarantee. So if you do something in the next notebook, we'll do this. If you do something like K-fold, where it just iterates through the data set and splits it, then you are going to get some that are only children. And then you've got a huge class imbalance. It's not well represented in your cross-validation procedure, and it's going to cause a big problem for you later on. So yes, that's a good question. We're dealing with it here, and I'm not talking about it here, but in the next notebook, we'll talk a lot about it. Okay. For the sake of time, I'm going to keep going. But if there are any burning questions, please raise your hand, or on Zoom, just shout at me. Okay, so for each of the kinds in the different ways to do functional connectivity, we're going to loop through. We're going to say, okay, we're going to do this as an entry, and now we're just going to collect the scores, the accuracy scores, because remember, that's what we decided to use as our metric. So we use our cross-validation to split our pooled subjects. And because this is stratified shuffle split, because it's accounting for groups, it also needs to know the group labels. So we pass those to them. And then we get a train and a test for each fold. For each one, we're going to use connectivity measure with whatever kind we set, correlation, partial correlation, tangent space embedding. And then we're going to compute the connectomes for the pooled subjects only in train. We'll fit the classifier using those connectomes, and we'll give it just the training classes, so it learns the labels for train. And then we make predictions using the test connectomes, so subsetting only the test ones. And then we store the accuracy for this cross-validation fold. So we say we're going to append to that list the accuracy scores for what were the ground truth labels, were they a child or an adult, along with what our predictions were based on the trained classifier that we trained on our training set. We're just going to do this. It's a big loop. If you run it locally, you'll find it takes a few minutes. So I'm doing the cooking show magic and having the result for you, which is that this is what happens. So we can see that in this particular case, the tangent space embedding is giving a higher accuracy. And in this case, red line is chance. So correlation and partial correlation, correlation's confidence interval, it's really a chance. But tangent space embedding seems to be performing a bit better. I need to emphasize, this is a super small example. In the real world, we don't want to do this on 30 participants for a number of reasons. But there's a paper that does talk about tangent space embedding, as I mentioned. So if you're interested in this in general, I would direct you to that. I will note in my own work, I don't do any between subjects classification. I only do within subjects. So I'm also very happy to talk about that. But these kinds of questions and problems are very transferable about how do you select the right features to go into your machine learning model. That's going to apply to no matter what neuroimaging data you use or think about. Awesome. All right, I think I have a few minutes left, so I'm going to do the last notebook. Cool. All right, so this is, now we've done what we promised, right? We said, okay, our core problem is we want to do machine learning, but we have neuroimaging data, and I don't know how to get from A to B. And NeuroLearn is super, super helpful to get from A to B. We've seen that we can take our data, we can use various nifty maskers, various regions of interest and atlases to get the data into the right format. And we can use also the confounds, filtering, all these attributes that we pass to the masker to try and think about signal versus noise in our particular data set. We can also then take all those measures and actually do machine learning. So we're done, right? Why are we still here? The lesson is over. Well, there's a lot actually that still needs to happen for machine learning, particularly when we're thinking about, applying machine learning to real questions. There's a lot of really hard decisions that we as researchers need to make, right? And so when we think about machine learning, I would say that everything we've done so far to date could be broadly considered as feature engineering, and there's huge scopes of feature engineering that I haven't had any time to talk about. but I'm happy to talk about later, like other forms of dimensionality reduction, like, subject selection, all kinds of things. But beyond feature engineering, there are many other challenges in machine learning quite broadly, which, there aren't necessarily great answers for, but we in neuroimaging are very lucky that we've had people thinking about these issues for a while, and we have some general guidelines for the kinds of data we're working with. So in particular, I want to point out that when we're applying machine learning, we also need to think about, one, the model that we train to generate predictions. So remember last time that we did a linear support vector classifier. I even called it a really simple model. There are many kinds of models that you could use here. I'm not going to have time to talk about those. Instead, I'm going to talk to you about another problem, which I would call problem 2, which is how do we assess the generalizability of our learned model? So how do we know that a particular model is useful in a broader context? And in particular, what I want to highlight is that this is not something that we as a field have done a great job historically about reckoning with. So this is a figure from a paper by Russ, who spoke earlier this week, and Grace Huckins and Gael, where they surveyed from 2017 to 2019 different machine learning uses in neuroimaging, in fMRI in particular. And what they see is that the majority of studies that they looked at didn't do any cross-validation at all, even when they were using machine learning, and they had very, very small sample sizes. And so, we are not necessarily in a position where everyone knows right away what is best practice when you're doing machine learning and neuroimaging. And because of that, I think everyone leaving this course will have a really good basis. But I just want to kind of hammer home why cross-validation is so important to think about, as well as different strategies that are in use for cross-validation with neuroimaging data. And I'll provide a couple examples about appropriate and inappropriate cross-validation within the development fMRI data set. One thing to emphasize is that best practice is always to have a separate held out validation set. I don't have that in this case, because I have a small amount of data. And I think actually a lot of investigators, it's really important to note, also have small amounts of data. In general, I would say the answer is collect more data. Go, and take advantage of the open data sets that exist and plug into consortium efforts and get access to those. But for this particular notebook, I'm going to assume you're just doing cross-validation. But in general, get more data, get a validation set. It's always the answer. So, okay, I'm going to do quick math. For those who, like me, find this a little bit helpful. But basically, the only point I really want to emphasize here is, why are we cross-validating? Like, what are we really trying to achieve when we do this? So we have N observations. Let's keep with development fMRI. In our case, we have 155 participants. And we have some variable Y, which in our case is going to be, are you a child or adult? A binary label. And we're trying to predict that from our data, which is, this high dimensional data set of whatever we've reduced the dimension to by time. Maybe you did an ROI voxel, maybe you did a connectome, whatever you did. So in general, you've probably seen this. The machine learning problem is we're trying to estimate some function that best predicts Y from X. So in general, when we have this function f hat that's learned on the training data, we want to minimize the error between the actual data and the predicted data. So this is a task, right? This is something that's already hard enough. What makes it harder is that that's sort of interesting. But what's really interesting is that we want to know if this generalizes to new unknown data. So, it's good to know that it works on our particular train test split, but we want to say if we get access to new data that comes from the same scanner, the same participants or anything else, as much control as much as we can, is this going to generalize to them as well? And so basically the problem is that we have many Y's and X's that we don't have access to, and we want to learn, or we want to know, is our function going to generalize to these Y's and X's that have the same characteristics, but we just don't have access to. So overall, what we're really trying to emphasize is that evaluation procedures have to test predictions of the model on held out data that's independent from the data used to train the model. Because otherwise you can perfectly learn this function within, and you're not going to get any access to, you know, on average for new samples, is this really going to generalize? The other thing is that if we repeat the train test split many, many times, we can also start to ask a related question, which is, given future data to train a machine learning method, on this case, on a critical problem, or, you know, whatever else you'd like, what's the error that I can expect on new data? So how well do I expect this to perform on new data that meets the same characteristics, but I just don't have access to? And that's kind of our overall goal. We want to know, can we learn a relationship that's going to generalize for this kind of data beyond this one sample that I happen to have?
Is it just, it's mainly fluorescent data MRI, because functional MRI, if you want to test or consolidate, it's going to be different tasks and it's difficult to find the right pattern.
Yeah, this is a great question. So the question is this generally just for resting state fMRI? Because with other collection types like task-based fMRI, you have to think about the structure of the task and cross-validation. So no, it is a general thing. It applies both to resting and task. And yes, when you're looking at something where you have a different data structure, like set tasks, you also need to consider that as well. That's just going to be a feature of the data. So I'll show this in a little bit, but effectively the question there becomes like, you know, how do I appropriately set up the problem such that I'm learning a relationship that I expect to generalize? Is it between participants that I expect generalization? So like, do I learn a model that works within one participant and then I see if it works on the next participant? That's a lot of what my work does, actually. Other models would say you learn a model on one run, you test it on the other runs. That's a little tricky because of what I'm going to talk about, where effectively you can end up with like data leakage because participants are going to be most correlated to themselves. So unfortunately, it's not just a resting state problem. It's a very general problem, and it does get trickier as you have more complex data. But there's a lot of really cool work trying to figure out how to deal with it. So my personal research focus is saying, learn on one participant, test on the next participant, but that comes with some challenges as well. I'm happy to talk about later. Cool. Awesome. Okay, so given that cross-validation is super important to allow us to achieve our goal, right, which is to learn some generalizable relationship, it's perhaps no surprise that a lot of people have spent a lot of time thinking about cross-validation, and so many different schemes exist across different domains, across different machine learning, you know, schools of thought. The scikit-learn documentation has a section just on cross-validation, which is quite extensive. So I would definitely encourage you to check that out if you haven't already. As I think Ariel mentioned in his tutorial, the documentation is incredibly didactic and could just be read as a textbook on machine learning, and would be an excellent education. So would definitely encourage you to check that out. But let's just showcase a few. So what we'll do is we'll compare a couple different cross-validation schemes in our own example data set. And because it's always nice to have more data, this time going to use all 155 participants. Otherwise, we're going to keep everything the same. So we're going to use the same atlas. We're going to use Nifty Maps Masker with the same parameters. We're going to go back to correlation. It wasn't the best performing, but it's pretty fast, which is going to be a nice trade-off for 155. Again, just to emphasize, this is not like something, you know, in a paper, different considerations in a notebook. Let's get it to run. So we're going to use correlation again, and otherwise we're going to have exactly the same procedures. So we're going to end up with this pooled subject array that we're going to use for our data. So as we talked about just a minute ago, in our classification sample, we used stratified shuffle split for cross-validation. And what it did was it preserved the percentages of samples for each class across train and test splits. So child and adult participants, excuse me, between each split. And to do that, it had to resample people multiple times. So if you had had cross-validation fold 1 versus cross-validation fold 2, you would end up seeing that maybe some of the same participants were in test across different folds. for example, to maintain the proportions. So this cell is just repeating exactly what we did. The only difference is because we have more participants, I'm going to increase the test size and I'm going to decrease the number of splits for computation. And so what we can see is if we do exactly what we did before, now we see this is the accuracy overall. So we have this accuracy, average accuracy across cross-validation folds, and we have a relatively small standard deviation around that accuracy. So this is the same procedure we did last time. We've just changed the number of participants in the test size and how many splits we did. Then we can generate a confusion matrix, which scikit-learn has really nice access to, like a quick display to do that. Confusion matrix display, helpfully named. And so we can actually see how did the classifier make mistakes. So this is what we want. We want the predicted label and the true label to match. So we want everything to be on the diagonal. So this cell is, it correctly thought it was an adult when it was an adult. And this cell is, it correctly thought it was a child when it was a child. I keep referring to Ariel's lecture about thinking about, you know, if you have males, females, coding them 1 and 2 is not super helpful. Similarly, coding adult and child 0 and 1, not super helpful. In this case, I know it's alphabetical. That's what it's doing. But in general, if you can, just code things so that future you will thank you. This is relying on a little bit of a hack. So we know here, thought it was an adult, thought it was a child. This, it got a little bit confused. It was actually an adult and it thought it was a child, but in general, as suggested by the accuracy rate, we're doing quite well. Okay, what if, as was brought up earlier, we forget about age groups and we don't account for those when we do our cross-validation fold? What if we just pull participants? We can test this by using k-fold, which doesn't explicitly stratify by group membership. So what k-fold is going to do is it's going to split the data set into k-folds where you set what k is, and then it's just going to draw from them, right? Use them for the train test splits. So in this case, we just say n splits is equal to 5, exactly what we did before. We don't pass groups because k-folds doesn't care. And we don't pass a random state because it's not shuffling. It's deterministically going to split it into 5. And when we do that, we see that not only do we have a lower accuracy, we have a huge range now around that. And if we look at our confusion matrix, you can see that it just so happened that on the last split, all we gave it were children. And it was like, do I have some adults in the sample as well? I think I do. So effectively what's happening is we had a shift, right? So it trained on a combination of children and adults. Then when it was tested, we only provided child connectomes. And so it was like, I can't handle this distribution shift between train and test. So it performs quite poorly. So this is both a point for think about your cross-validation schemes, and also however you test your classifier, look at the confusion matrix, look at what it's really done and the decision that it's making. The other thing this exercise shows is the limitations of the accuracy metric. So accuracy is how we've been defining how successful our classifiers are, but there are many, many different ways that you can think about it. Yeah.
Sorry, I have a question about the splitting of the groups.
Yes.
What point would you recommend, like how unequal would the group sizes have to be for you to recommend like upsampling or like downsampling from certain groups, like a little bit more equal?
I see. So sorry. So you mean in the case of like, I have the data and not even in the cross-validation scheme. You mean just generally, like, how do I account for these? Or
So when you have like different size groups,
Mhm.
you know how sometimes people will apply something first to kind of like upsample from the smaller group so that then you have more equal size groups and then you can run
I see.
classification on that.
Yeah.
Like at what point of kind of inequality of the sample size of the groups would you suggest doing that versus something like this where you're cross-validating on the proportionally same number of groups? Does that make sense?
It does make sense. Yeah. So, I mean, GB has a really nice paper about importance reweighting, actually, which I think is part of this question, which is like, if you have very divergent sample sizes, so this happens a lot, for example, where you have to do preferential sample selection. So say I'm really interested in some disease state that's rare. It's a rare disease. So I just don't have access to it. And so I'm going to sample from who I can get access to, and maybe only have like a few rare disease state cases, and I want to see if it generalizes. So in that case, you could end up in a situation where effectively, like, you're not, if you cross-validate proportionally, you can't have really any data in your cross-validation folds. Like if you only have one rare disease state or two rare disease states, like you're in a bit of a tricky spot. There you can get into things like importance reweighting, where effectively you start to take a more causal perspective on the data that you have. And I had stuff in here on this, and looking at the time, it was good to remove it, about like confounding in the sense of causal estimates for when you learn these models. But one of the things would be group membership if you have access to a very small amount. So that's a very long answer to your question. The shortest answer is effectively like, if you can still form meaningful cross-validation folds and ideally still have a meaningful validation set, then you have enough proportional data to do this, even if there's some imbalance. But if you have extreme imbalance, like if you only have access to a handful of examples from your rare disease state, but you have many more healthy examples, which you need to train machine learning, you need many examples, then you need to think about other schemes, because you don't have enough of your disease state of interest to form cross-validation folds where there's somewhat balance within the folds. Because then, yeah, then you could end up in a situation like this, well, like this, where it just predicts whatever the dominant class is effectively, and it would have great accuracy, but it wouldn't tell you what you want to know. So yes, let's talk about that later, because it's a super hard problem, and sometimes the answer of just go get more data isn't satisfying, because it's really hard to do, and then you have to just think about, like, ideally the causal structure of what you're trying to model and how you can get closer to making inferences on it. Yeah.
There's a question in Slack.
I can launch Slack again.
Oh, I can ask. The classifier code, do I use the variable connectivity to be able to map back to the ROI? If I'm interested to learn about the regions that contribute more or less, not sure I get that information.
Sure. Okay, so here, for example, you can do view connectome, and that's actually going to put it back on the brain, and you can see all the nodes and edges. Ooh. This was a bit more meaningful when it was less. Also, you can look here and see all the nodes and edges for each particular relationship, but I'm not sure if that's, do they mean after the
In
like,
the classification.
Sorry, can you hear me?
can you hear me?
Hello?
I guess you can't hear me. Can you hear me?
Yes. Yeah, I mean, after I ran the classifier, if I want to see, like, if I want to use this for more of the biological meaning from.
I see. Yes. Okay. That's a great question. So effectively, the question, as I understand it, is I have learned a classification pattern, and I would like to look at the feature weights. So I would like to make inferences based on how the different nodes or edges or voxels or whatever, you chose as your dimensionality reduction scheme, map onto the classifier. So there is a way to do that. I'm not showing it because there's a lot of caveats that I would have to give with that. Effectively, it's very, very difficult to make strong inferences looking at feature weights for a variety of reasons. One of them is like, you may have, for example, we try and clean up head motion, right? But there are different strategies and they have different success rates. And so you don't necessarily know if the feature weight that you've returned is going to allow you to make the inference you want. Similarly, you can see this if you look at variability across cross-validation folds, or even across cross-validation schemes or classifiers at an extreme. Like, you see a huge amount of variability in what the feature weights are. So there's a way to do it. There's a way to map back. We have a couple examples in the documentation, and I'm happy to point to those for how to do it on voxels really easily. But it comes with a lot of caveats that I don't know that we have time to totally go through today, but I would just like point you towards to be cautious as well when you consider that. But it's a great point, because yes.
Thank you.
Yeah, for sure. Okay. Yes.
We can point to important, vital importance.
Yeah.
I can give you what variables are really important, the feature are really important.
Yeah, so JB is mentioning the idea of feature importance, which is a bit distinct from feature weights. So you can do something like permutation importance, for example, where effectively you permute a given feature, and then you see how much your metric that you use to establish your classifier, like accuracy or whatever else, changes as a result of that permutation. That is one strategy. It's a very expensive strategy, so I know people don't necessarily love it computationally, but it is one strategy that you can use as well. That maybe, yeah, has slightly more guarantees on how you make your inferences. I'll say it like that. Okay, I want to leave a few minutes for questions, and I have a few more cells. So let me try and get through this, and then let's just chat. Also, I'll be here for the next week, so I'm always happy to chat machine learning in that time. Okay, so one of the things I mentioned was accuracy isn't necessarily an ideal metric, right? We just saw that because it was just predicting one label, and it seemed like it was still above chance. So other metrics that we can look at, for example, are the receiver operator characteristic, or ROC curve. And here I'm going to show you the ROC curve for our stratified shuffle split model, because our k-fold model has an undefined area under the curve since it's only predicting one value. So this is what it looks like for the last fold of our stratified shuffle split. For those who haven't seen ROC curves, I find them a bit confusing to interpret at first. I really liked this lovely illustration from Wikipedia. So here what you can see is this dotted line is just giving you a random classifier. And on the y-axis, you have the true positive rate. So I'm correctly labeling things. If we go back up here, you have the true label and the predicted label. So when they align, you've got the true positive rate. The false positive rate is when you're saying something is a case when it isn't. And what you see is that the ROC curve is going to vary ideally somewhere between your random classifier and a perfect classifier, which would have 0 false positive rate and 100% true positive rate. And so our classifier is doing pretty good, actually. It's on the upper end for sure with the stratified shuffle split. Because again, with the k-fold, we only predicted one value, can't really plot it in this case. We can also look at the variability of our learned model across cross-validation folds, which is something that's really nice. So here, what we're showing is one standard deviations in gray. The different folds are plotted in very light colors, and then the mean curve is plotted in dark blue. So you can see that across cross-validation folds, we are seeing variability in our prediction, which is useful to know. Right? Okay, so probably the last thing I'll have time to talk about before we break for questions and lunch. I know I'm keeping you from that, so I'll show you something. Hopefully that's not too much of a downer. Is that when we think about cross-validating, we have different schemes to do it. Obviously, we've talked about k-fold, talked about stratified shuffle split. We've shown some variability in the cross-validation folds and tried to emphasize that that's important, because if you want to make inferences, you need to know this variability exists. You need to think about how you can make inferences in that context. One other thing that's really important to know is that when you do cross-validation, again, more data is better. So what we see is that this is from a paper by Gael and colleagues a few years ago, where basically they look at the difference between cross-validation with varying strategies on varying amounts of data. and a held out validation set, which again is the gold standard. And effectively what they see is that if you have access to more data, then you're going to see a tighter bound. Because otherwise what ends up happening is if you have less data, you can have a really wide confidence bound around your estimate for how, accurate or useful is your classifier. And that isn't a fault of you, it's just an interaction between the large sampling noise in neuroimaging data. So all biological data is noisy. It doesn't matter if you're using fMRI or anything else, biological data is just noisy, right? So that's a characteristic we have to deal with. The other thing is that if we provide relatively small sample sizes to the classifier for our train and test, then what we see is that noise can be quite dominant because we just don't have enough data to learn a stronger relationship. So I just want to replicate this idea by systematically decreasing the size of our test set. So remember, we started with 30 in this notebook because we used all 155. So if we drop it to 15, we see that before we had an accuracy, I believe, of, let's check so I don't lie. We had an accuracy of 94 plus or minus 0.2%. Now, when we drop the test size in half, we have an accuracy of 95, but we have a wider standard deviation, 5%. And then if we drop it just to 5, we see a drop in accuracy and an increase in our standard deviation. So 0.84, 8%, right? So if we look at the distribution of accuracy scores across cross-validation schemes, this is all again for the same method, it's just for differing sizes of the test set. You see that the smaller your test set is, the wider distribution of values that you're going to get for a cross-validation. And again, this issue of like, how do I make inferences is critical. And when you have a really wide distribution of errors, it's harder to make inferences. So the larger data sets that you can supply, the better off you're going to be. I don't know if that's a downer or like a rallying cry for data sharing. I choose to interpret it as the latter, because we do need lots of data to fit these models and to make inferences on them. The last thing that I wanted to point to is just that, if you're using train test split where you have information that could carry from your train into your test, you need to be really careful. So we think about this a lot in the context of, and I think you may have been told this already, or just know this already, that if you do, for example, some processing steps like mean centering, you don't want to do them on train and test at once, right? You don't want to do this kind of processing where it's shared and could lead to data leakage. You want to do it just on the right parts separately. And in neuroimaging, one of the things that ends up happening is, in addition to these concerns about processing steps, we also have to worry about whether or not data in our training set is highly correlated with data in our testing set because it's, for example, from the same participant. In that case, you need to be really careful because what can end up happening is that you can see really inflated estimates in your cross-validation set compared to, again, the gold standard validation, because effectively what's happening is you're getting leakage because you have information about one participant in train. And, even though you are correctly holding out something and putting it in test for them, the information in train gives you access to things you don't necessarily want to have access to if you want to make inferences on your classifier. In our data set, this isn't a clear problem since each participant was only sampled once. But this is something to think about, particularly with complex designs or longitudinal designs. And just to show you, scikit-learn is great because there's also just you could set K folds to K being the number of participants, or you could call leave one out and it'll do it for you. And you run that and you can see, again, we have a reasonable accuracy, but a very high standard deviation, which is because this is a binary label. You're either right or you're not right. So I think that was everything I really wanted to say. And 5 minutes left. What questions do people have? Yes.
I have a question about kind of like what you were saying at the end about
Yeah.
like the within subjects versus like between subjects and that classification?
Yeah.
Because, so like, I do functional MRI and like most of the like papers and stuff that they do doesn't have like, you don't often have like 15 subjects. Most of it is like within classification. So just like wondering, like, with this issue of like even if you're leaving data out with it, like within the same person, is it still like if you have like much more, if you're using like trial based, like so you have much more samples within that one person, is it still like kind of better to aim to do like a between subjects classification, or is it like so appropriate to do it within if you have like much more, like yeah, just wondering your opinion.
Yeah, no, that's a great question. Okay, so the question I think is like, if you're in a context where you have relatively few subjects, but you have a lot of data for each given subject, given this issue of, how to define train test split in an independent way, does it make sense to do within subject in that case because you have so much data, or should you still be aiming for between? I think it's a great question. I think it depends, in part, it depends on your goal, right? A lot of what I've talked about today, we keep alluding towards inferences. And I think it comes back to that, right? So if your goal at the end of the day is to say, I have 4 participants, I have a deep sampling data set, and I learned 4 models, and these are the 4 models for those participants, and like, this is the accuracy each of them did separately, and that's the inference I've drawn. Then, that's a very different situation from saying, I want to learn a model that is going to relate 2 different tasks, for example, and it should generalize across participants. If you're in the latter case, you really need to think about, including between subjects cross-validation, because you want to test explicitly that between subjects nature. If your goal is never to leave that one participant, then it doesn't make sense to do between subjects, right? So I would say it sort of comes down to what you want to do. A lot now with these very dense sampling data sets, I've seen many people who just say, I want to make a model, I want to make 8 models for my 8 participants, and I'm just going to publish those 8 models, and that's all the inference I want to do. And I think there are very clever ways to do that as well. Yes.
I was just wondering, the example you showed was about functional imaging, but is there any reason not to use this on other connectivity modular, like connectivity, it's like structural connectivity or fusion-based or any other, once you've reached the point where you have a connectivity matrix?
Yeah, that's a great question. So the question is, the examples I showed were in fMRI. There are obviously many other neuroimaging modalities. Is there any reason not to use this on those kinds of modalities? So I'll say NeuroLearn is really focused on, MRI. So it's fMRI and structural MRI is also handled in there. But in general, NeuroLearn is really focused again on this kind of feature engineering aspect. Like, how do I get from the images to data that can go in machine learning? If you have a way to get your data to go into machine learning, and I know Ariel and many others in this room have some really great ways for diffusion, and there are lots of other ways for other modalities to get it so it can go into machine learning, that's all you need. So NeuroLearn will help you for fMRI and MRI. There are lots of other packages that will help you for other tools. I think we'll hear about M&E from Liberty in the next couple of days, which will similarly help you with EEG and MEG, and also developed by a team partially overlaps with scikit-learn, so plugs in there as well. Whatever your data is, so long as you can get it into the right format that you can start interacting with scikit-learn, then all of this will apply from notebook like 2 and 3 on. Yeah.
Thank you for your time. I just had a question about, so with your examples, we were looking at the binary classifier. I assume that this would easily extend to, like, let's say if you wanted to classify into like 4 groups or something. How then would that change? Like, would you be able to still plot ROC curves, and like, how would that change like what we do and like what other?
Totally. This is a great question. So the question is, everything I did was a binary example because zeros and ones are easy. But obviously in real data, we'd like to use more complex things where we have multi-class problems. And I would say, yes, so the general framework that I showed applies. So you can have a broader confusion matrix, you can still have an ROC curve, but I think that what's primarily going to change is the kind of classifier you do. So I was doing this linear support vector classifier, and there are different strategies. In the case of 1 versus 1, that's really what it's designed for. If you have multi-class, then you have, there's a really great illustration that I don't know how to access quickly, but effectively you have this question of, do you do 1 versus the rest of the classes? Do you do 1 versus 1 and then combine all the 1 versus 1 pairings? That's primarily what's going to change for that particular classifier. There are other classifiers that you can use that are better designed to handle multiple class labels. There are some strategies, as I'm saying, in SVC that you could think about, but that's the main thing that immediately triggers that would change. Otherwise, once you sub in the right classifier, the rest of the framework should hold. Yeah.
Thank you for your thought. I have a question for, because for my project, I'm also working with a clinical population, and when I look at the prognosis, it's quite imbalanced. And after reading different things, I ended up discovering imbalanced cytokine.
Yeah.
So I wanted to ask if you have some comments on that, if the field is kind of starting to use that, and if you have something that is.
Yeah, just on the issue of like dealing with class imbalance quite broadly. So I think this is something that, yes, machine learning is thinking about as I think a broad community, because there are many, many scenarios where we have class imbalance, right? And a lot of the tools as they were originally developed were developed in purely theoretical fluffy land where everything is beautiful, and not in real limited data sampling settings. So yes, definitely something people are thinking about. I would say the reason it's in scikit-learn imbalance and not scikit-learn proper is because, again, as was alluded to, like these methods are changing and growing, and they're not yet tried and tested in the same way that like a support vector classifier is. But there are some that are generally regarded as quite promising. So I think, as I mentioned, JV's kind of importance reweighting is one idea that people have if you have clear causal estimates of like what the groups are that you need to, or the features that you need to represent. But there are others as well. So yes, definitely something people are thinking about. There's definitely best practices that are emerging, but I think for our data, I haven't seen anything super conclusive, although maybe you're working on it to profile all of them. Yeah.
Just to follow up. So for example, because you said that it's kind of not, it's not really tested and kind of shown how it works. Would you advise that, for example, I run the models with this imbalance package and then I compare them to the balance and kind of to have
no, sorry. So I think what I'm sort of curious about is there are different imbalance, there are different like schemes by which you could address an imbalance. And I think they sort of assume different characteristics of the data. And I haven't seen a good example where for neuroimaging data, they compare many, many different rebalancing or reweighting methods. I think there's some really promising ones that I would really be interested in seeing compared, but yeah, I'd be curious. Right.
Sorry, I have another question.
No, it's okay.
So am I correct in understanding that like when we were looking at the connectivity matrices that they're ROI by ROI, so we're basically like I guess reducing an entire time series into one matrix, is that correct?
Yes, so you're getting whatever you defined as the connectivity measure, the correlation between the time series or the partial correlation, or yeah.
So my question is then, is there a way that we can, or like, I don't know, maybe like what strategies can we use or like different methods to use to like then incorporate like time as I don't know, I guess not a feature or a variable?
Yeah, that's a great question. So it really depends on the inferences you want to make. Like for example, we've done some stuff where we do inter-subject decoding. So we train a classifier on some subjects and we see how it applies to held out subjects. And in that case, what we were using were beta maps from like a general linear model that we fit. So we said, here are beta maps for our different conditions from our different runs for our different participants. And there, you don't have a sense of time in the same way, but you do have like a map for every stimulus type for a run. So you have the whole voxel map rather than just an ROI. You could also think about, I mean, there are people who think about like connectivity in a dynamic sense with like dynamic functional connectivity, right? And there are many, many different strategies there in terms of like how you choose to create your connectome and how you choose to window, for example, how it changes over time or state space model or anything else. So yes, you can definitely incorporate time. It depends. This is one of those, it depends on your data. It depends on your data and it depends on your question, but there are definitely ways to give you more resolution than just one matrix for a whole run. Yeah. I think we're past, so thank you all. Let's get lunch.